Okay, thanks very much for the invitation. A pleasure to be here as always. Uh, I'll be talking about stuff we've done over the past many years, but in particular about a paper I just put out yesterday, uh, where we do the following. So we try to make a model there, a bit model, which can show how you will get all unitarity and so on, which with a black hole like you want. And you also will feel no firewall if you're a freely falling observer. So the question is, of course, what happens to the kind of arguments that the firewall crowd was making, that you must feel a firewall. And the issue is that you have to see how you define complementarity, under what conditions do you want it, and do you want it for a freely falling observer, or do you want it for a guy who's freely falling, but also for a guy who locally hovers near the horizon and picks up stuff. Okay. So if you want someone to be able to hover and see stuff like at zero velocity near the horizon, and maybe also for guys who go in, so like you basically want the vacuum in every sense. So you can't really have that, because after all, what did Hawking tell us? I mean, Hawking told us that if you have a vacuum there, you're going to get pair creation, and you have the entanglement problem. And then if you don't want the entanglement problem, then of course it's the same statement saying you can't have the vacuum. So if you really want exactly the vacuum there, that's going to be difficult. But the idea of complementarity that we've had for many years, which came out of how we were looking at the actual black hole states, these fuzzball states, was that you shouldn't ask for that. That's asking for too much. So first you have to see how the information comes out. You have to know what the structure is at the horizon, and I'll show you the fuzzball construction. It shows you a surface there which actually reads information. And then if you're a freely falling observer who comes and smashes onto it hard, for those guys and only for those guys, let's ask for complementarity. The idea we use to get this complementarity is similar to the spirit of ADS-CFT, and it's going to be an approximate complementarity. The bigger the black hole, if you freely fall onto it, the harder you hit when you reach the horizon, and your accuracy of complementarity is better and better. Okay. So we'll adapt the ADS-CFT fundamental idea, but an approximate version of that would come out, and that sort of makes the picture. And I'll show you a model of sort of bits which will try to realize this picture. So please feel to be as critical as you want about the crucial idea, because what I would like to know is if anybody can find a hole in it. So it's not like I'm trying to ask you to believe the steps. It's just a picture. If you can actually find a reason, look, this can't work for this reason, then please catch me and let me know. That's what I'd really like you to do. So I'm here for the weekend. Please catch me and see if there's anything that you can see will never work. Then it would be great for me to know. So let's just begin with the information paradox. You take a black hole or some star, it collapses, makes a black hole. Then you get the entangled pairs at the horizon. And at least at this leading order, you can see the entanglement just keeps rising. So at the end of endpoint evaporation, you have a problem. So the way I would like to think about black holes is through this thing which we now call the fuzzball paradigm, which has roughly 4 loosely connected parts. I've just called them A, B, C, and D, so I can just roughly review them, and then I'll get down to the actual complementarity issue. This step D here was what we thought should be complementarity in the fuzzball picture. So this is the picture we had around 2010, 2011. And then in 2012, the AMPS argument said, look, if you have information coming out, which we do get from the other steps in this construction, then you can't have D, you can't have complementarity. And when we came back and looked at it like, well, what went wrong? We thought we could get complementarity. The answer seems to be that what AMPS assumed about how the black hole behaves and how they want complementarity is different from the assumptions that we had made. So that's the difference I want to show you. And let's see if we can see that with this modified definition of complementarity, if everything works, then I would like to propose that that's the way one would like to think about this. So this is just a very brief summary to start with, then we'll get down to the real stuff. So what's the fuzzball construction? I put it all in one slide, so we can just, I'm thinking that people have seen this before. How to operate this? So at weak coupling, you may just have some state in string theory. Let's take a super tube made of maybe D1 and D5 branes or some branes. And then as you increase the coupling, what happens is places which were near the super tube, the metric develops around this. But where the super T was actually running, you get more redshift in the places which were in between. And so if you plot the metric, it develops a little kind of pit, obviously, but the places which were near here, they get sort of deeper in, the places here get a little shallower in. Anyway, but it never actually develops a horizon. So that's the kind of thing you find. It never actually develops a horizon. So all the states in string theory, when you take them to strong coupling, you never actually get what you might have naively thought in normal gravity, that you may get a throat, then a horizon, then an interior to the horizon, then a singularity inside. All this doesn't happen. The whole thing just ends before the horizon. And if you try to see what really happens around here, you just see that all the region around here, if there was a compact dimension, it just comes and closes off like this, making a structure, in this particular case, like a KK monopole. So in fact, the space smoothly comes and closes off here.
Samir, can you just remind me what the current thinking is regarding the curvature scale on those geometries?
Yes, so the curvature scale here, according to me, should always be Planck scale for a generic geometry. So absolutely.
Planck scale, yeah.
Planck scale, yeah. Because otherwise, I don't think you can get all the scales. So this is supposed to be some really quantum mess here. There'll be fluxes here. There are states we know where there are strings when you try to do the PP wave kind of states. You can have all kinds of mess here. So the point here is not that you can actually do anything with these states, but the point was you never actually get this whole region here. Okay.
But isn't that region somehow the ensemble of all these very Planckian things?
So in some way, if you can average this and get this, is that what you're asking?
Yeah.
Yeah. So I don't actually, so that's part of the issue that we want to discuss today. Is there any way in which you can recover this in some approximation? Now you can't actually average different metrics. If I give you a metric G1 and a metric G2, I can't take G1 plus G2 upon 2 because you don't even know which point in one metric corresponds to which point in the other metric. So it shouldn't be that kind of averaging.
But in the Euclidean case, for example, where we have a smooth geometry that caps off, not talking about horizons, that's supposed to be representing some sort of thermal ensemble, I thought.
So here, I actually have a particular state. That's the whole black hole, a particular state. When you make a black hole by collapse, you have one particular state. It's very quantum, it's very messy. And right now, I don't have any averaging. I just have one state. So the question is, will there be some effective behavior of this which can ever mirror this? And the claim would be that under certain processes, it will mirror this. And if we try to average this where it becomes this for all processes, it will never work. So I think it becomes a question of, it's an effect. This interior should emerge as an effective description for some things that we do with this. And those some things will be that you fall freely onto it hard, and then something will happen here, and this should be an effective behavior. That would be the conjecture. Not like you can prove that, but that's where we are trying to go.
So when you said the curvature is Planck scale, is that true in the weak coupling string regime where you actually explore these explicit solutions?
No, once you get to Planck scale, you can't. So let me just tell you what is actually done. So what you do is you take all the states. So let me just first say, so it goes back to all earlier stuff. There was these works on Maxwell rotating solutions in these papers. And then, so if you take some very simple solutions, you find that if you take a Maxwell rotating solution, it never has a horizon, it caps off. And after a while, you realize that if you take things which have maybe no net rotation at all, still locally it behaves like a Maxwell rotating solution, so it always caps off. So basically, you always sort of keep ending up here. So you start with very simple state. Let me just go to my next slide, which maybe has the answer to what you're asking. In the CFT, you have all these. This is the D1, D5 CFT. If you've seen these pictures, the details don't matter. If you have random excitations going up and down these strings, you get all the states in the CFT. But you can take simple ones where the states are all, let's say, all these strings are in the same state. If you do that, it's like taking a photon gas where all the photons are put in the same state. It becomes like a laser, and you can get a better classical approximation. It's not perfect, but the corrections will be much smaller. So you make those guys, and as you put them into more and more different states, you sort of split them into more complicated things. It gets more jagged the way I was showing you, and then you just leave the argument there that in the CFT, there's no sharp distinction between one state and the other. They all make a family. You take the simplest states in the CFT and you start going down, and they look like what I was showing you. And then, but because none of them are developing a horizon, just getting more jagged, as they get more jagged, in the end, there's nothing you can do about them, but you just let it be there. So it's an argument which suggests that finally in string theory, we've actually been able to find a mechanism to end the state outside the horizon rather than have the no-hair theorem in which you keep falling in. So there was a nice paper of Gibbons and Warner from a couple of years ago where they went back and explored why we were getting these guys, because Gary Gibbons was very interested in knowing how come the no-hair theorem was beaten. It was there are so many theorems before. And it turns out it's all because of the fact that firstly you have higher dimensions. If you're in 6 dimensions, the solutions is non-singular. Torus was removed first. But so let's say if you're in 10 dimensions, it's non-singular. But if you first, if you look at it as a reduced 5-dimensional solution, I'm doing the Sturminger for black holes. If you take 5 non-compact dimensions, the projection is always singular. You can see, for example, if you get this KK monopole kind of thing, which was discussed in Lewin Malthus and Mau's paper, if you have a KK monopole kind of structure, in the full space, it is non-singular. But if you take the projection onto the space where you live, there's always a singularity. So that's the way Noether theorem sort of went past. Yeah.
So the solutions, they don't have horizon at all.
Yeah, there's no, see, it ended here, right?
Yeah, so what happens if I, say, try to shine light through it? So will it get absorbed there, or it will pass through?
Yeah, it can't pass through. There's no place to pass through.
It will go back out, right?
It will go right back out. But that's what we're trying to explore. Because
the energy of the light.
Yeah, so that's the point we're trying to get. Depends on the energy of light. Because if you put a little bit of light, and this is like a very simple solution with a big curvature radius, the light will come and go out. That's true.
Okay,
right?
so it behaves completely different from black holes in this sense.
Yeah, right. But now the point is, suppose you take a very generic state here, like the kind of things we really won't talk about, and you send a high energy beam of light in there, then it's actually not going to move in that background. It's going to take this particular state and jump it to many other states. Right? There are many neighboring states because the entropy of these things, of course, is very high.
The size of these objects is what, again, Planckian, or it can be bigger?
No, the whole size of the object will be the same as this horizon radius of the black hole. That's the point. It's a large thing. It's a large object, right? It's the same as the horizon
The
radius.
statement of jumping to another state, I mean that, naively if you take this geometry and you send in some light, you create a black hole in the interior.
A black hole in the interior.
Light collides with the structures you have there in the bottom and creates some singularity.
So that's the question. If you create just a singularity there, then you would make a black hole, right? But the argument I'm going to make is before the threshold of that black hole formation, all the other possible states of this kind that you could have, take the ensemble of all fuzzball states, the amplitude to disperse into those is more than the amplitude to actually make the black hole. And so the wave functional actually goes there. So I'm glad you asked that. That's going to be the key point. Let me just say that once again. The key point is going to be that the number of these states, because they're going to be given by the Beckstein entropy, and that's a very large number, somehow I'm going to just play with that very large number all through the story. And anytime you come near the threshold of black hole formation, what you have to ask is the amplitude to drift into one of these other states. There is a path to go there. Okay, that one can check. There's a topological path to go there. There's an amplitude to go there, which I'll estimate. I'll have to multiply the probability of going to one of these states by multiplying by the number of states I have. And the goal will be to show that that probability will exceed the probability of it to actually continue in the naive classical way. And that's how we're trying to solve the problem.
You're using a mixed language of classical solutions and quantum transitions, things like this.
Yes.
I mean, I should think about this as a quantum mechanical system.
You should, yes.
And therefore it should not it's not always possible to think about them as classical geometries, as far as I'm...
It is what?
It's not always possible to think of this.
You should not.
Classical
I never like to think of, absolutely, you should not. I mean, I would really encourage you to always think quantum mechanically for everything, right? I mean, so exactly as I said, if you just take, black body radiation in this room, if you put all the photons in one state, you'll get a laser which looks close to classical. The corrections are 1 over n. You break it in 2 different modes, they are 2 over n. You break it to the generic value, it's order 1. So all we do in this game is do the simplest ones and ask you to go down the chain mentally yourself. Okay. Assuming that there is going to be no phase transition in the whole category, because the CFT has allowed us to list all the states in a listing. You start with the simplest one, you make the next simplest one, you can make it. After some time, the fluctuations are becoming bigger. But the claim here is, or the hope or the conjecture here is, that at no point new physics will be invoked. And we just want to say, however messy they get, it's not like some new non-local effect arises or something new happens. Whatever quantum mess we get, that's all we have. So the state really goes and ends at that horizon in some messy way. The other region never came out.
In the picture, if I just had a Rindler horizon, should I also view that somehow as a course?
So it's very important the Rindler case, for me, will come out to be different from the black hole. But in this effective complementary behavior that I'm going to get at high impact, they will become similar. So okay, I'm glad you asked that, but let me just take 1 minute to say something and then maybe I'll divert from that for a moment. See, Rindler is what you get from the limit where Minkowski space has 0 mass. Right? So when you draw the picture in 2D, it looks like, that's like a black hole. They both look like this. But Rindler space is what you get in the limit of m equal to 0. Like
m
empty
equals infinity.
So that's the point. The other limit in the black hole case, when you get to Rindler, it's m equals infinity. Right? And what we're going to find from this is that these two limits are not the same. So essentially what's going to happen is that as the m becomes larger, the number of states you have is a to the m square. And so what we're going to find is there's a small amplitude transition in any process to one of these states. Multiplied by the e to the m square, that amplitude becomes order 1. So the amplitude to go into these messy states which you're now seeing will become order 1 because of the multiplication by the e to the m square. So that's why we normally think that the Rindler thing just decouples, that locally the black hole has to look smooth, but the m equal to 0, exactly as you said, there are two different limits, right? M equal to 0 and m equal to infinity. These are very different limits. Because m equal to infinity, there's a huge degeneracy of states, e to the m squared. And that's going to come and make the two things not the same.
So Eric, yeah, I think I kind of agree with Eric that you're not really taking these geometries that seriously. You're just talking about quantum states.
Absolutely, just quantum states, always.
Then, can we just replace fuzzball by microstate?
You can call it microstate.
What does fuzzball add to microstate? How is it different?
So this is actually a construction of microstates with no horizons. That's all it is.
And they have
So if you take a general theory, you wouldn't find
geometries and some approximation.
Shouldn't you be quantizing the coordinates of these solutions to produce, at least in the weak coupling description, to produce quantum states?
I don't know if you will get all by quantizing just the simple ones, because, for example, we know states where you have to actually put a string in it. Right? I mean, when you start writing all the duals down, okay, we have whole classes of them where we take the CFT, make the guy. So this is the things we worked out long ago after the PP wave stuff that Juan was doing. You can take, if you want to excite things which are both left and right excited on this string, and you have more than one pair of excitations. If you have one up and one down excitation, it's a graviton. If you have two up and two down on the same string, it's actually this string sitting there. So for lots of states, you can keep identifying various categories. And all that one is saying is that as you go through the categories of the things you know, in all the different corners of the states of the CFT we know, we never actually got something which looks like this. And so the conjecture is you don't actually ever get this. You just get a mess of this. Okay? So,
sir, but if you say that the typical microstate of the black hole is not described by the fuzzball geometry, or the quantization of the coordinates of fuzzball geometry, then what is the actual use of the fuzzball geometry?
Yeah, so the use is right here. And in fact, in the next step, which I'm going to tell you, so the use is that you've actually managed to be able to make a construction where, in fact, you've broken the no-head theorem. So you have, what you've done is you've taken the whole family of CFT states, you start with the simplest one, and the next one, and the next one, and for them, when you actually find the gravity duals, they don't actually have the horizon.
Sorry, but you're not, I thought you said that you don't expect the typical CFT states to be of this form, to be described by the quantization of these solutions.
You're not supposed to quantize them as semi-classical quantization, right? The point is, where's my slide? As you go to, so let me just try to understand what you're asking. You try to write down all the states one by one in a sequence, starting from the simplest and going to more complicated ones, like you do for a black body gas. Okay?
Sorry, are you saying there's a precise map from the CFT state to the fuzzball solution?
So in principle, there is a map. I'm not supposed to find it. I'm not even trying to find it. Right? I'm just trying to give you an argument which is supposed to tell you that in string theory, you can actually break the no-head theorem.
But when you say map, you mean a map from one set to another set, and you have to tell us what both of the sets are.
I think what you can do is you can forget about the fact that the curvature is becoming large. So all the solutions have finite curvature, and you can quantize these collective coordinates. That's essentially a string.
Yeah.
And then the charges of the black hole and so on depend on the energy of the string. So there will be then a one-to-one map between these are for the BPS cases. So there is a one-to-one map between the BPS states and this geometries.
Where you produce
all the BPS states?
Yeah, all of them, yeah. Again, all of them will have, curvatures of order and flank.
Yeah, this was a non-BPS one. This was a PP wave thing. These are non-BPS. But in principle...
Non-BPS, if I understand correctly, we don't have the generic solutions.
No, generic you would never be able to make any useful construction. But the only argument was that this is supposed to give you a process of understanding. If simplest states that you can make have no you try to make a conjecture that now in string theory you can get all states with no horizons.
So if I take a state that corresponds to two states that correspond to two different classical solutions, are those orthogonal quantum states, or are they like over-complete coherent states?
If you do that, you'll get over-complete coherence. There's nothing different about this than you would get about any normal system.
I have some issues with the counting. If I think of the classical solutions as parameterizing an overcomplete set of coherent states, then counting them is not counting the dimension.
But that's not how you count them. For example, for the simplest ones, which were called the two-charge extremal states, there's this paper by Richko where he actually quantized them and counted them. So how do you quantize it? You take the space of these solutions. In that case, you can actually take the classical manifold and try to quantize it. And then you set up this Witten-Chernkovich bracket on it. And then you count how many states there are. You get the right number.
So you do the counting in quantum mechanics.
But absolutely in quantum, because that's you have to do that. So this is not supposed to be actually, you're not supposed to actually make the states, make them reliably, or do any of those things.
I mean,
This is just supposed to show you that you could actually have hair in string theory.
I mean, one thing you could imagine is to start with this situation and then change the values of the moduli at infinity, so that the actual calculation is in the supergravity regime of all these states, and that also gives you counting. This is the more or less standard BPS counting, where you go between weak and strong coupling, and you find the representation that makes sense and where you can do the counting. And then in this case you can somehow track continuously where all the states are doing and what they're becoming at the finite curvature. That's all for the BPS case.
Sorry, but what class of BPS black holes can you actually produce the black hole entropy by this by quantizing the possible solution?
Yeah, I don't think I actually ever want to make all the states and count them. I know that Binar want to try that. I hope they succeed at some point.
So the ones for where the statements I made apply were for the D1, D5 system.
Yeah, that one can be completely solved. Yeah.
I mean, there is some entropy, but no classical entropy. So
it's not D1, D5P.
It's just the two-charge.
D1, D5P is what Binar wanted trying to finish off. They got up to the right order, but not the right coefficient. But I think, let me just clarify what one is trying to do here. Maybe then I should maybe move on from this. People often ask, how reliably can you make all the states? Can you make the states? Can you make them and count them? That's not anything to do with what we want to do with this. For example, even if I gave you a planet like Jupiter, I wouldn't ask you to make all the states and count them. Okay? Because nobody's ever made a single state for Jupiter with any reliability, nor have I ever tried. And if you ask me to try, I would never be able to do the job of counting them for you. What you're trying to see is, you're trying to fight against a problem we had all along in black holes, that if you actually take the black hole metric, the Schwarzschild metric or any metric you like, and then you try to quantize a scalar field around it by solving box phi equal to 0, and you expand in spherical harmonics, look at solutions f of r, ylm, e to the I omega t, you find the solutions f of r are singular. So you can't actually find quantum modes which you can then populate with creation operators and so on to make all the neighboring states. You get a unique vacuum around the black hole. So that is the no-head theorem we are trying to see. Is there any way to ever beat that? And in string theory, all you find is, hey, this is interesting. You take all the CFT states and lay them out. Start with the simplest ones that you can understand. At least for those, you can come and take a look at what's going on. And the simplest one, in fact, as I said, in maximum routine solutions where this capping off was seen, you can just see what's going on here. In these simple cases, all these strings were exactly in one state. Okay? And if they're all in one state, this is a two-charge thing with all the strings in one state. Okay? The geometry is going to be very classical. And what is it? It is capped. Then you go to those where they are not one state, but let's say broken into two categories. And what is it? It has a cap like this. So you keep breaking into it more and more pieces. You know that as you get to the end of this process, they're all covered because the CFT can list them all. Okay? But on the gravity side, these are getting more and more messy. If you ask me, what are they becoming? I don't care. I can't do it. There's no way I can quantize them. Okay? So the only state I can make them or quantize, I don't want to do any of those things. This is simply supposed to show that in string theory, it seems plausible to assume that this doesn't happen. That's all that this was supposed to do. So if anybody asks me, have you made all of them? Have you quantized all of them? No, I just want to make one or two, just to see that I can break the no-head theorem. And as I was saying, what Gibbons and Warner found was there are reasons why you can break it, because if you try to do it in 6D, in 5D they look singular, in 6D they are smooth. If you take a reduced solution down to 5D, the Lagrangian actually has a Chern-Simons term, and the Chern-Simons term was never used in the no-head theorem.
But you didn't break the theorem. You're just studying a case where there is no theorem.
That's the same. Yeah, there's no theorem here. So why was there no theorem here? And that's because of Chern-Simons term in the Lagrangian. Yeah. So they were never checked with Chern-Simons theorem. Chern-Simons term. Okay. So the statement of the first one is just very simple, that we are not going to invoke any new physics. Okay, not any new. All that we are going to say is, okay, they just become messy. But apart from becoming messy, they don't do anything new. And let's see if we can solve all the black hole puzzles with this. That's the conjecture. Okay. If somebody, so not everybody was, of course, immediately happy with this, because you can say, hey, we made a big change at the horizon. But so maybe Maybe some states are fuzzballs because you checked a few, but others are black holes, okay, the kind of thing that you were worrying about. Okay, so I have done nothing about it. That's it. You can say that at this point, yes, absolutely. Or as you go to more generic states, the messy fuzzball may just approximate a black hole. So, there may be some tiny, tiny changes that you can't see, and it may go back to a black hole. But then, of course, in these cases, either these cases you should ask, then what's the solution to the information problem? So people are not very happy with the complete change of the horizon this thing was suggesting, and should we be happy or should we be worried about that? So one possibility is that, even though you have either this or this kind of basically traditional black hole, there could be some subtle corrections that at leading order things work out, but at subleading order, this is Hawking's thing, a particle pair comes out, this guy's entangled with this guy, and the entanglement keeps rising like I had on the first slide. But you could have subleading effects at higher orders, and because there's so many quanta emitted, if you actually collect all the subleading terms together, there are m over m Planck squared quanta really emitted. If you then try to compute the entanglement of everything outside with everything inside, maybe the entanglement really goes to 0 because this dominant term was rising, but its subdominant ones may actually make it come all the way down. So I want to begin with this, just reviewing this little theorem that I had some years ago, which proves that you can't do this. And the reason I'm doing that is from there we'll go in various different directions, because everywhere you go from that, you have to either add an assumption or break an assumption. So I'll just show you that. And in going to the AMPS argument, you have to add an extra assumption, and the whole difference will come with that extra assumption. Okay, so AMPS will go from whatever we're going to do here for this theorem, they will add one assumption, and I'm going to later on argue that that assumption maybe shouldn't be there, or at least the first that assumption is not true, and so we will not actually be able to rule out complementarity. Okay, so this was the theorem. So if this is just a cartoon of a black hole, and here are the quanta which have been emitted before, B1 was entangled with C1, B2 with C2, and so on. But now a new pair is coming up, and what do we assume? Inside the black hole, we make no assumption. We have no clue what's going on. Far away, we assume everything is normal. So a lot of things that people are suggesting, like, these very interesting things that Suska and Malzina was suggesting that, there could be non-local connections. Right now, I haven't done that. So this is normal physics. Here I just say it's approximately normal physics, which means this region should be like the room, but there could be small corrections. That's the kind of thing we were after, right? So there could be small corrections. So the small corrections are called approximately normal, but otherwise it should basically feel like this room. So at leading order, the pair comes out in an entangled state. You guys have heard this so many times in this room, I'm sure. I'll just pass over it quickly. So at leading order, this pair is entangled with nothing else, so its S is 0. And if you just look at the entanglement of this pair, C which came out, it's log 2 because C is entangled with the B. So leading order, you can just calculate that. And if you wanted to approximate what you get, if so say there are small corrections, then this one, it was 0 before, it can go up to some small value, let's call it epsilon 1. And this was log 2 before, let's say it can at most change by an amount, epsilon 2. So here actually I should say one should really compute this a little carefully, because the size of this epsilon 1, epsilon 2, they depend on the dimension of the Hilbert space at each emitted step. So here I just taken a 2-dimensional space. Steve at some point was working with 4-dimensional, and Steve every checked the 4D case. But this depends on the dimension, and something of the kind that Papadodimas, Raju are doing, they're trying to hide some non-local effects and high energy correlations. It's this number that they can then try to change with some new assumptions. Okay, so suppose you assume the small corrections do only this and this to you, then you can plug them into this amazing strong symmetry inequality. You take some steps in this way. I won't go through it slowly because I'm sure you've seen it before. I've seen me talk about it here before at some point also. And then what you find at the end is that the entanglement of the outside with the inside at step n plus 1 is equal to the entanglement you had at step n plus log 2 minus at most this amount. So it exceeds all this minus this. So in fact, the entanglement will actually keep rising. So in fact, in leading order of Hawking, it was going like this. And at most, you can lower it by epsilon 1 plus epsilon 2. So you can only go slightly under, but you can't actually make it turn over.
Sorry, it seems to me that there's another source of small correction that has not been considered, which is the Hawking at different steps. The Hawking pair production process. What if they're correlated? So if you have some earlier Hawking quanta being
no, that has been included. That has been included. That's the point.
Why is that included?
Yeah, that's exactly the point. Because these epsilons that are coming out at every step, they are not fixed numbers. The epsilon at every step can depend on everything that happened in the past. That's the point.
Okay, but well.
See, otherwise there was nothing to prove, because you really want to entangle everything with the past.
Sure, but you're making some very strong assumption on the actual form of the quantum states being exactly.
No, so I didn't write the whole proof here. So I'm sorry, I didn't actually write the proof here. But let me just tell you what was supposed to be here. I gave you the whole proof. You would write the state as the leading order one plus In the subleading order, I would put, let's say, the orthogonal state, which is 0, 0, minus 1, 1, and 0, 1, plus 1, 0. That's all the 4 ones that, for example, Steve was looking at, right? So I have 4 states, and the coefficients of all the other 3 are, let's say, less than some epsilon 1, epsilon 2, epsilon 3. And all those numbers are small, but they can all depend on everything that happened to all the previous states.
Aren't you assuming that there's exactly no entanglement between late and early Hawking contact?
No, everything, but that's how you get the entanglement. That is where the entanglement
He's trying
is.
to derive that by saying that the radiation which is produced by the Hawking process should come out like this, step by step, up to small corrections. And then what he shows is if that's true, then what you said can't be true. That can't lead to large entanglement between the early and
The small corrections is the correction to the entire. You're really considering the all small correction to the entire quantum.
No,
state for all the Hawking contact, or just for this pair?
It's corrections to the pair.
Right now it's to one
consider
pair.
the Hawking photons that come out
Well, I'm saying that's not enough. I mean, why is that enough? Why can't you?
That's because that's the whole power of this, right? Because this proves that at every step it's not going to go down.
That's what I'm asking is that in the assumption of the actual quantum state produced in the Hawking process, are you taking into account or not the possible correlation between the step n and step n over 2?
He's running the logic the other way. So he's saying that if at each stage what you have is close at the level of the quantum states to what Hawking says, then you'll never produce entanglement between late and early Hawking radiation. So you could run it the other way, and you could say, therefore, if there is late entanglement between the early and late Hawking radiation, then this has to be violated by an order 1 amount.
Yeah, let me just write the conclusion down, I'll show you. But yeah, so I'm sorry, I sort of assumed that people sort of had seen this before, but I'm happy to sit down and take you through all the steps.
But they're assuming a very special form of the, let's go, I mean.
No, I didn't actually write down all the form.
Out of effective, I mean, you can sort of address the stuff.
I understand come out of the standards, because I argument based on effective field theory, but.
Yeah.
Well, another way of stating it is if
there
you
is
want
an assumption in this discussion that Bn, Cn, and all these things live in some Hilbert space.
Right.
Absolutely, yes. All that is going on.
That's,
and that effect,
That's right. And so those are, one by one, we can break all those and try to see, where you go.
No, but the technical point is, if you assume a Hilbert space structure, the argument goes through just fine, even if these, quote, epsilon corrections that Samir is talking about include correlations between the outgoing members of a given pair and all the other pairs that added earlier.
The epsilon is
There's
dependent
no
on
assumption that the state of a pair is pure to some high approximation.
Yeah, but isn't there the tacit assumption that the feedback on the metric can be neglected? That
Yes,
the background
that's right.
can be neglected.
That's right. Yes.
So
Apart from the gentle evaporation of the whole.
You can't expect to understand the true nature of the process until you begin to calculate the feedback on the
So,
he's
so let's
supposed
half
to
there and half not.
including the flux of the negative.
Yeah. So one is just assuming that the semi-classical approximation is valid. And one is just assuming that as the black hole keeps evaporating slowly, at any one time I can still use the semi-classical approximation for that metric. And then the Hawking evaporation of the next pair is working on the evaporation, or is working on the background of the black hole with that mass. That assumption is there, right? And I think that's what you're asking about. That
You're going to assume that until throughout the process?
Until near the end point of
Until it's
evaporation.
Planck sized.
So it's just to show that small corrections to the normal Hawking argument won't work. So somewhere you have to make a large correction. You could say that if you want to say that after the black hole evaporates, after some part, it's a completely different structure, good. That would be a solution of the problem, right? But then you have to show what other structure would be, because that would need some hair, like you have to get some other structure to the black hole. So yes, if you want to find some other structure to the black hole, you say after a quarter of the black hole evaporates, changes to some other animal, good. Then we just want to ask what's that animal? Is that a new kind of structure? If you have no-hair theorem, what can it be? But if you always have the no-hair theorem and you haven't found a way to beat it, then all you can have is at any stage of the black hole's evaporation, you have a black hole of that much mass, and you can only get wave production on that particular mass at that value, and then it doesn't do much apart. Then it includes everything in here.
Well, when half the mass is gone, you haven't made any correction to the background in your...
No, you have. You have. Because when half the mass is gone, I'll do this evaporation on the metric, which is for the black hole of mass m by 2.
Yeah.
I'm not doing the original metric. So just like Hawking would have done. Right? But I'm just trying to put small corrections to Hawking process. Hawking would also have slowly evaporated the black hole and made it smaller. Okay, I don't have anything else useful to say about it, so maybe I can just, but I'm happy to catch you later and maybe we can talk about it. Okay, so the claim from this was at the end you find that if the Hawking radiation has to be pure and no entanglement to the whole, then if you really want to get information to come out in Hawking radiation and there's no new physics like infinity is sort of not separate from the inside of the black hole or anything like that, then you have to make a correction of order unity, and in some sense was supposed to complete the rest of the fuzzball argument. Like you're not going to make all the fuzzball. People are asking, are you sure everything is a black hole? Everything is a fuzzball. There are no black hole states. Why can't some of them be black hole states? But this shows that whatever you have, unless you put in some new physics, you want a correction of order 1 for the low energy Hawking modes near the horizon, and the fuzzballs are doing it for you by changing it completely at the horizon anyway, so why not take the fuzzball? So it's just an argument which sort of completed the philosophy of the fuzzball. Okay, so that's why I said it's just complement the fuzzball construction. You are anyway changing the horizon, and now you shouldn't argue so much about changing it because you need an order 1 correction anyway, otherwise you couldn't have solved the problem. So from here you can go in different routes. As I said, you could, let me just skip this because these are the different things you can do. If you do Papadopoulos-Raju, you can change one thing in it. The Steve Giddings says you can keep the high energy modes unchanged, but modify the low energy modes. I want to in particular talk about the amps thing, which adds an extra assumption. That's the one I want to maybe focus on a little bit next few minutes. Effective field theory should be valid for something which falls in until it reaches the horizon of the black hole, within one Planck length of it, which is called the stretched horizon. So I sort of wrote it like this. No novel physics is encountered outside stretched horizon. Okay, this was my interpretation of how it works, so I just put question marks on that. But under this condition, assuming that this is how I should use it, the argument of amps was you'll get a firewall, which means no gentle infall, and certainly no complementarity. And I'm actually going to show you how you should actually think of complementarity a little differently, and you will get fuzzball complementarity. This assumption actually has a hidden catch in it. And it's that catch which actually, so you can't actually find that something is, you can't, if you just use the whole bit model and the strong subvertivity, I don't think you can get anything, this is all you can get from it. That the low energy modes have to be corrected by order 1. Okay? Because those are modes involved in Hawking radiation, this is all you can see from it. And that's why you have all these options. For example, if Steve wants to change only the low energy modes and not the high energy modes, you can do it.
Samir, can you be clear about the distinction between there's also high and low angular momentum. So are you, I mean, there are low frequency modes with very high angular momentum. Do you think that those are also screwed up?
Low frequency with high angular momentum.
Yeah, like whose frequency is of order the temperature, but whose L is, large.
In the fuzzball picture, they presumably do, since you have scale curvatures.
So amps would have said that the ones with high angular momentum, but omega of order the temperature are also not in the entangled across the horizon in the usual way.
So I didn't get the what is the question?
Well, I'm asking, are you always talk about high and low energy modes, but I'd like you to always make your statements also telling me about the angular momentum.
Okay, so I'll draw a picture of what I mean by high energy, and maybe at that point I'll think about it again. It's not like I particularly think about the high angular momentum here, but I'll try to come and answer the question.
If I understand correctly, what you are saying is you need to change the modes that have energy of order of the temperature and can make it out to.
That's right.
Yeah, that's.
So if the high angular momentum doesn't make it out, then this theorem doesn't tell you anything about them.
Okay, but amps also argued that the high angular momentum ones.
That's right. That's right. Yeah. But so that's right. So
well, that's one way of doing it. I think there's a better way of arguing, but yes, they use mining targets.
So I'm agreeing with that, right? I'm saying that from this strong side, if you do nothing else, if you add no other assumption, you can't actually find exactly as Juan was saying. The only thing you can find is that the modes which are actually going to make it out as Hawking radiation, they are corrected by order 1 in the entire process somewhere from, I think I wrote out very explicitly, if the normal evolution from 1 meter to 3 kilometers for a solar mass black hole, that has to be altered by order unity, and let me also add S-wave because they are the S-wave ones that come out. That's all that you can actually prove with this, right? Because I was using only the Hawking modes with this. And now we're going to add an extra assumption which AMPS put in, and then the conclusion will be much stronger that, you are going to necessarily get burnt, and that's the one I want to talk about.
Yeah.
So let me just get to that one. Yeah, I haven't said anything about that, so it's true. Higher L hasn't been talked about. Okay, so let's go and see. There's just one more step I'd like to mention here, which I had roughly talked about, but let me just say it once again. The idea that we have is that the way we're going to get all the new effects that we're going to talk about is that if you take a collapsing shell, there's some amplitude for that to actually transition into a fuzzball state. They are quantum states, just like Eric was asking. So you can actually find an amplitude transition from here to here. And in fact, using some work with of Cross and Wilczek from the past, one can actually estimate that now. and one finds some particular kind of rate for this, and it's, as you can imagine, very small, because a macroscopic object is transitioning to another macroscopic object during the process of collapse. It can always happen, but the rate, of course, is going to be very low. Why would you then even think about it? And the only reason is that there's, in fact, a very big number hiding in black hole physics, and that big number is the degeneracy of states, which is e to the s Bekenstein. In fact, you find these numbers just take each other away. So in earlier papers, I had actually tried to estimate the action, and there was a coefficient of order 1 alpha over here, which I didn't know how to estimate. So there was always a question, if the suppression is e to the minus 2s Bekenstein, and the degeneracy e to the s Bekenstein, they won't exactly cancel. But then using this cross and with check calculation, which is, it's a 30-page paper, so it's not like I can explain all the details of how it worked in any easy way. But in the end, you find this is actually, the conclusion was very straightforward. You actually have a coefficient 1 here, and then you see this actually exactly cancels.
How is this different from a normal thermodynamic system, this argument?
No, the numbers are the same. But the point is this number, e to the s spec, is very big for the black hole. And so what we normally don't think about is that the transition from this collapsing shell, firstly, if there were no other states like fuzzball states, which you don't have if you take 3+1 gravity without the extra compact dimensions of string theory, I don't have the fuzzball states. Then there's nowhere to go to. There's no transition amplitude to even ask about. If you have these states, let's at least ask if I have a shell which is collapsing, is there any amplitude transition into this state? I can at least ask the question, right? If I ask the question, I have to then compute the amplitude for transitioning, some kind of a rate. And then after I ask the rate, I have to also say how many states there are, because you multiply the degeneracy of final states, and all one was saying was the observation that those numbers cancel. So this is just a picture.
For which black hole is this computation done for?
This was a short shell black hole. I have not done for anything. Actually, the cross and with check thing is done for short shell, for things with charge also, but I have not actually tried to play with that.
So
it should work the same way.
What kind of possible solution are you talking about here for the short shells?
So I should have said that before. The conjecture now which I'm using here to do everything with complementarity and everything, I'm now assuming that every black hole has the kind of structure which we found from the near extremal story. Okay. It just doesn't.
There are theorems that say that's not true, right? I mean, for the Schwarzschild thing, the no-hair theorem is actually a theorem. So there's
no, it's gone for the same reason. If you look at the Gibbons-Warner paper, it has nothing to actually do with being near extremal. It just has to do with the fact that if the Lagrangian has a Chern-Simons term, there is no no-hair theorem.
There's no quantum states. I mean, the question is, can you have a quantum state?
No, he's very careful to alternate back and forth with the context.
When you're talking about a no-hair theorem, it's a statement about a classical action. These states have higher derivative corrections, and there's no point in talking about a no-hair theorem at the level of these supposed geometries. Yeah. It doesn't make sense. You just assume that they exist in some structural form and see what kind of...
But then aren't we back to just saying that they're microstates?
Yeah, microstates. So that's the point.
They are microstates. I agree that if you make a black hole, it's going to be in some microstate. If you make it in a microstate.
If you have a black hole...
Yes. Can I say something? Because this, I think, is... Well, it's been a key point for me, and I think there might be some confusion about it. Everyone believes a black hole is made up of lots of microstates. Okay, so what's the difference between a typical microstate and what Samir is saying? I think it has to do with the size. Intuitively, I mean, I had always thought that you take matter in some pure state, it's in a particular microstate, you evolve it, it collapses, it somehow gets, the size of the quantum state gets well inside the Schwarzschild radius, and the exterior geometry is to a good approximation the usual classical black hole. Okay, so that's a microstate, but the geometry is still essentially to leading approximation of black hole. Samir is saying no, that in string theory at least, microstates, when they collapse, will always stay of order the size of the Schwarzschild radius. You never have a classical horizon in any approximation around it. So it's a microstate, but it's bigger than you might have thought.
But sorry, one is talking about properties of classical solutions with extra sources, extra dimensions, and geometry.
The classical solutions, I don't like calling them hair anyway, because they're solitons. There's no black hole. There's nothing. Okay. There are lots of solitons. Certain people have been finding them. Okay. I don't think that's relevant, and Samir says that's not the key point, because most of them are Planck curvature anyway. You get all these corrections. They're all quantum mechanical. The key point is the quantum state, and how big is it? I'm not even sure it's well defined to ask the size of a quantum state in quantum field theory.
You can ask when the semi-classical picture of geometry stops making sense.
Okay, but is there evidence that these states are this big?
Well, certainly in the supersymmetric case, there is evidence.
You meaning these solutions?
These solutions,
Based on
BPS.
They're classical solutions.
They're the classical solutions, but they are representing certain quantum states, right? They're coherent states or something.
But you
for
see,
certain simple
you're
things.
using solutions as evidence in a case where you know the solutions don't exist. That's the thing that's driving me crazy.
So Samir
Okay.
started
sorry
this
for-
talk by saying that he had a picture he wanted to describe, which had
Yeah.
various parts, and he was not going to justify each particular point in detail. He wanted to know if there was any reason why it couldn't work in principle. So I think you're holding
That's right.
him
That's
to
all
a
I'm trying
higher
to do,
standard
yeah.
than he was claiming at this point.
Yeah, that's all. I'm just trying to say whatever happens for extremal and near extremal,
There's no
let me just assume it happens for the far from extremal, and I just want to put out a picture there as to how that's consistent with getting your fuzzball kind of approximate complementarity, because you have to understand the notion of approximate complementarity.
I mean, if you don't like the description in terms of fuzzballs, maybe you could say the following thing, that you consider a black hole, instead of having the horizon, you have some kind of wall, and you have the thermal atmosphere at all the way to the Planck scale. So that reproduces the entropy, and so fuzzballs are a specific construction.
So I think that the extra thing I would add to that is that, when you normally take the atmosphere, you could say that even for the 3+1 black hole in canonically quantized gravity with no extra dimensions or anything, right? The new thing which is happening here is that as you come near the horizon, you can imagine these gravitons will interact, these thermal gravitons will interact with each other, and nonlinear effects will come. And in string theory, the special thing that is happening is that the nonlinear effects are leading to a new topological structure where, in fact, if you had a compact dimension which is coming all the way to the horizon, it just caps off exactly like this KK monopole.
Why is that important?
Because if you don't actually end the thing here, the important thing is that you can, if you just had the normal thermal atmosphere, which you see in Schwarzschild coordinates, you go to Kruskal coordinates, the whole thing continues, there's nothing there. That's the whole key of every problem, right? But here what's going to happen is, if you come like this, like a cigar, and you close off like this, okay, there's no space-time after that, there's nowhere inside to go. So it's a new topology. So the claim is that all the solutions, let me just try to draw here a rough analogy which I sometimes use in a colloquial level talk. This is the Witten's bubble of nothing. So there you cut out a region from the middle of space. You need a compact dimension. But as you come near this on from any side, it just closes off. So in fact, there's no space-time here. So this is a different topology from empty space, which of course was happening. So the claim is now that the topology of the black hole is such, all the black holes are such, that in fact the compact dimensions come and space-time actually ends outside the horizon. The inside is gone. The only difference here is that because this is just an extra twist here, these are your KK monopoles. You can put a plus for a monopole, minus for an anti-monopole. From every different direction you come here, this is a Planck scale. At every Planck scale you have one bit. I'm talking very roughly. You could choose a plus or a minus, and those are all the states of the black hole.
Sorry, I want to follow up on Daniel's question. If a microstate doesn't have a semi-classical geometry description, how do you measure the size of the microstate?
So it's not a question of size. The point is, so this is how you measure the size, right? Yeah. The entire outside of the horizon, the whole space-time ended here. So the size is this, because it's like a bubble of nothing whose diameter is equal to the size of the whole thing.
That's a picture, but if you want to actually calculate some observable, what is the observable that would detect the size?
You mean this size or the size of
this is the actual metric?
Well, I mean, whatever the size that Gary says is.
I mean, I think there's a little cross purposes here, because these are very interesting solutions with interesting topology capping off, as you say, but that's all the classical solutions.
Yes.
Right? And I think what you want to say is that this is a special case, that generically we may not have classical solutions looking like this. Yes. So I wouldn't emphasize, if I were you, the topology and all this space-time capping
that's right.
off.
That's fine.
Generically, you expect it just to be some quantum state.
But that's right. So let me just then say what I would say about the quantum thing here. So for example, this is the bubble of nothing is what Witten used to say that Kaluza-Klein space with the extra Kaluza-Klein direction space is unstable. Now in there, of course, the compact circle he was using, if you normally ask somebody what's the size of a compact circle, you'd say Planck size. Okay. Typically think of a compact circle, the extra dimensions being, let's say, Planck scale. And if you do that, okay, then somebody may say, why was Witten drawing this? Because after all, if this is a Planck scale curvature, we don't know anything. So then somebody could come and say, look, we haven't proved anything that the space is unstable. But I think the way that people think about this, or at least the way I would like to think about it, is you take this thing to be, let's say, 100 Planck length, and then you have a thing whose curvature is not Planck scale, or 100 times that radius, and then you see there's this problem. And then you say, okay, if I have this problem, if the compact dimension is really taken down to 1 Planck length, plausibly the problem still exists. And you're saying no more than that. Okay? So you make the ones which are, you make the compact radius as, one was saying, take your moduli such that you can make it nice and smooth. Then you take it down there, and then you conjecture that nothing changes in character, because as you take it from 100 Planck lengths down to 20 Planck lengths, you can see that you're not actually changing the character, it's just becoming little more larger fluctuations. And then you assume, without proof, without anywhere being able to prove it, that when you get it down to 1 Planck length, it becomes something quantum and messy, but doesn't go back to the vacuum. Exactly what you would have said for the bubble of nothing, there's no more about it than you can say here. I'm not even trying to say that. If you ask Witten how to actually make the quantum state of the Planck scale cap over here, and then try to prove that the bubble of nothing was doing something, obviously you would not be able to. So that's all that you're trying to do. You're trying to show the solution. There is a new topology. Till you find a new topology, you still have the old topology that has the no-head theorem. But because in this theory the new topology is allowed, there's a whole class of solutions here. And because there's a whole class of solutions, now you have a new conjecture possible that in fact all the solutions live in this category. And for a simple thing like two-charge extremal, you can actually show that. For other things, it's progressively more difficult. But because you're making a conjecture as to how the picture should work, that's all, as I say, that's all I'm going to do right now. So okay, I haven't gotten very far, so let me just take a second. But that's fine. This is exactly how I would like to do this anyway, because we're getting all the points out one by one. This is just a picture I want to tell you. I want to show you a little bit more reason as to how this comes out in later slides if I have time. This is a horizon. This is a shell. Shell is trying to come to the horizon. But this is the physics we are after. As the shell comes closer to the horizon, there's a transition amplitude for it to go into these fuzzball states. So as you come a little closer, the amplitude now starts drifting over here. As you come even closer, more of the amplitude starts drifting. And in fact, by the time the shell comes here, the amplitude is all gone out from the shell. If there was no fuzzball states, the shell would be here, it would be here, it would be here. There's nowhere else to go. And in fact, then you can analytically continue, and you have the inside of the Penrose diagram. Okay. So this is just one second, I'll take your question. So this is going to be a crucial factor in everything which I'm saying, that if you actually have these other solutions, this other topology that I just mentioned, these analogs of the bubble nothing, if there are many, many bubbles of nothing that you can make, as the shell is coming to the radius, where the bubble of nothing mass is the same as the mass of the shell, there's some amplitude for the shell to transition into this bubble of nothings. You have to check if there's a topological path, then you can check. Okay? Now, once there's an amplitude transition there, you have to multiply by the number of possible bubbles of nothing you can have. Okay? And suppose that number, then the small amplitude for transitioning and the number of states you can transition, suppose they cancel out. That's what I'm trying to show this cancellation over here. Then this is the picture I'm trying to say. Why does something happen at the horizon? That was always the question. What happens to something coming near the horizon? This is what I would like to argue happens as you go near the horizon. The amplitude is drifting into configurations that in a normal theory of gravity you wouldn't see, but in string theory they are like these bubbles of nothing, and I would like to argue they exist, and this is what they do. And there were several questions. Let me just take that.
Yeah, so I understand the picture, but what specific calculations support this suppression, this formula for the...
Yeah, I'll go show you that. That's something I did. It uses old work of Cross and Wilczek. We just used it. I'll say something a little bit about it. There were a couple of other questions. Yes?
Are you thinking of these as a sequence of static configurations, or is this shell falling across the horizon?
It's falling. It's falling. As it's falling, it's transitioning. Okay, good. Let me try to say something about that. There's nothing very deep about this that I'm trying to say. If you take any of these fuzzball configurations, they are just, you can just imagine them to be quantum eigenstates which just stay there, right? They are bubbles of nothing, just going to stay where they are. Okay? Now, if you take a shell which is collapsing, you can make this state of the shell as a linear combination of these states, which are going to make a complete set of states in this basis. As you evolve, your amplitude just drifts into other linear combinations, and the whole thing just spreads out in this fashion. So this is really a time-dependent process, but it's simply evolving just like normal quantum mechanics. You have some states, they have slightly different energies. Each state evolves with a different phase, and that's how things normally seem to evolve in any quantum mechanics, and that's all that's being done. So you're evolving into the eigenstates of the fuzzball, but the progression from here to there is just the way anything spreads over different eigenstates because of the spread of energies. So nothing. Let me just go on, because I just want to get to the main point, and then maybe we can come back and take a question, because I'm already at the end of my hour. So this is the point which we want to talk about now. How do you get complementarity now? Because you can't go through the horizon, right? There is no place to go. It's a bubble of nothing. There's no place in there. You can't go through. So why didn't we say right away that, if you fall into this, you'll crack your head and die? In fact, Yusuf Bina always said exactly that. If you ever heard of Yusuf Bina talk about what happens when you fall down the throat of a fuzzball, he always said you'll crack your head and die. Okay? Yusuf Bina has very strong language. Okay? So I just put this picture to just mirror what Yusuf would actually say. So why wouldn't we immediately say it's a brick wall or a firewall? And the reason I wouldn't have agreed with Veena, and in fact we've debated this over the years, the last 10 years off and on, is because I always hoped that you could get some kind of complementarity. So what kind of complementarity is one thinking about? Okay? So to get the basic idea, I want to go back to the idea of ADS-CFT. And so I just think about it in the following way. I don't know that everybody thinks about ADS-CFT this way, but since Juan is here, we can ask him. So if you fall on a concrete slab, it's clear that you're going to break your head and die. So nobody probably doubts that. Okay? Now, what happens if somebody gives you a stack of D-brains and asks you, do you want to fall onto that? Are you going to feel okay? Are you going to be worried? Okay? So in one language, you'd be worried. If you only read Polchinski's papers on D-brains about how you get converted closed strings joined to open strings on D-brains, you can see the guy is getting his closed strings are getting converted to open strings, and looks like he's being very badly torn apart. So it looks as bad as a concrete block. Okay, so if I give you a choice of falling headfirst on a concrete block or headfirst on a stack of D-brains, you might not be sure which one you want to choose. But actually, in this case, if you were a string theorist, you would know which one to choose. Because in this case, if you had these D-brains, whatever is going on here, you could convert to open string, and the open strings then spread out here and so on. Actually, it's a very, very faithful representation of all the energy levels that you had in here. And in fact, all that is happening here is that you'll fall here. You can replace this thing by a throat, right? The D-brains by a throat. You'll go in, and then further in. So if you actually want to fall headfirst onto something, and you have a choice between a concrete block and a stack of D-brains, you should choose a stack of D-brains.
This is a true test of faith.
It's a true test of faith. But I have the faith. Okay, so I would have the faith. So what is?
Sorry, can you comment on how your energy here compares to the energy of the barrier? Like when you're down in there, do you think you're living in ADS space, or are you?
So this is the ADS throat for me. This was the neck. This was flat space. This is the ADS throat.
Well, but I mean, there's a big barrier there. So if you have an energy which is of order the ADS scale, and you try and fall in from 10-dimensional flat space, you'll just bounce off of the barrier and find yourself back in.
True.
I think in the ADS language there is a cutoff, which is when the energy at which you connect to flat space.
Yeah.
So this guy has energy
bigger than that. That's what I was trying to ask.
Yeah. So I understand there are two regimes. I just drew this cartoon because I wanted to show you a cartoon right here. Yeah. But you know what I find most interesting about this, which I've never completely understood, so maybe I'll just pose it to Juan and maybe we can talk about it offline at some point. You know, normally you think of the wavelengths at which you want to throw things in to get the whole normal ADS-CFT game. The wavelength should be larger than the diameter of the throat. Lambda should be more than root Q. But you know, as a matter of fact, if you actually take a little string and you throw it onto these D-brains, like just take a little loop of a string, which is string length, it will actually break up into these pieces, of course, as we know. But in the dual picture, still floats in completely smoothly because the string is much less than root Q. It's always been a bit of a surprise to me that I don't understand it in the same level as I understand the rest of the ADS-CFT, because in principle, it's a different energy scale. But it works equally well. And I don't completely understand that, but because it is true, I think it's very interesting. So even if you take this guy is very much smaller than the root Q, right? So that's exactly the question you were asking. Normally I should think of wavelengths, if this is the diameter of the throat, I should think of wavelength this long, and then 90% of them scatters back, the 10% that goes in. Let's talk about that. That's how the early absorption calculation D-brains were all done. But if you take a small string and you throw it onto the D-brains, it will get absorbed, we know that. But will the string feel pain, feel hurt? You can imagine yourself being made of strings, right? If your oscillation frequencies distort, you'll feel pain if they keep the same. But we know that they won't, because even though you can't actually do this calculation, a little string loop falling in here, I think we all agree to just go in. So it's very amazing. You fall into a stack of D-brains, even in the limit that you don't normally think of, the decoupling limit. You will fall on your closed string will fall on the D-brains, it will break into lots of open strings, and you will feel nothing. I'm happy to fall onto a stack of D-brains. I have faith. I'll be okay. So I find this little surprise. Okay, I just find the whole thing very interesting, that if you are not an ADS-CFT person or not a string theorist, I find it very hard to convince people that this and this is different, because you can see this happening, right? But what's really happening is, in the end, not mysterious for us, because we understand what happened here. What happened is you got a faithful map of all the Hilbert space here onto a Hilbert space here. So if you're actually expanding in this direction, it's a very, I just drew it on the next slide. So here, if you just take a graviton, let's not have the person on there anymore, it's a little cruel. So this guy just keeps, in the CFT, the bubble just keeps expanding, but it's not an arbitrary state. It's a very particular state, and the spectrum of excitations here exactly maps onto this. So as you keep going here, you keep going in, and it's perfectly okay. Yeah.
So you should make sure that every mode that you consist of is corresponding to some transition in the states of the black hole.
Exactly, that's the point.
Otherwise,
that's exactly the point.
Otherwise, part of you will stay behind.
Absolutely. So that's the key. That's exactly the key. If the level density here wasn't very high, then every frequency which is in the person That's what we want, right? Every frequency in the person should find a possible frequency here to go over to. Now, in the concrete block, that doesn't happen. You have some energy levels. This has some other energy levels. Some resonate and get absorbed. Some don't get absorbed, and the wave function is distorted.
But how do you know that a person consists only of such modes? I mean, if
So in this case, what happens is because of large n, the density of modes is very high, and so you can see that you have an accurate map is possible, right?
You're somehow just in the regime where the black p-brain solution is a good
Yeah, I
description
think
of
you need
what's going
strong
on.
coupling. And
Yeah, so it's very strongly coupled and...
I'm using all that.
Yeah, GN is large.
GN has to be big in order to not feel pain, but then your first picture is not...
because I haven't used G in here.
Yeah, the brains kind of fatten out and...
right, and if GN is small, this is going to be a Planck scale throat, you're not going to feel so good.
Right, then you'll feel yes. Yeah, so right now I'm only trying to understand how it could have worked, because it doesn't prove that it will always work, right? I could give you a high amount of level density, but some states may not transition properly into their corresponding states. So it's obviously necessary to have a high density of states. It's not sufficient, right? Because that's why it's so non-trivial that it works, because I can give you lots of systems which have very high density of states, but unless every mode in the infalling graviton is exactly going to map to its corresponding mode with the same amplitude, it's not going to work out.
That's only probably a necessary condition.
Exactly, that's what I'm saying. It's necessary.
Because if you have a mode that goes in and goes that way and one that goes that way, and those are different,
That's what I'm saying. It's necessary but not
particles
sufficient.
in your body. You don't want that either.
Right. So exactly. So it's necessary but not sufficient. For it to be sufficient, there's much more going on here. Right?
Sorry. So if there is this smooth way that you don't need to change any frequency for that spin to hit the D brain, why do I have to have a singularity later?
Say that again.
I mean, why do I still have a singularity in a finite proper time?
You mean in the black hole singularity?
Oh, you don't.
I haven't come to that yet, right? Right now I'm just going into the neck here. The horizon and singularity is what I want to talk about.
I understand. I just feel like I don't quite like
why. There's no singularity here.
Yeah, this is
just a particular example. Been there. You can ask the question later.
Yeah, I haven't gone down there. That's what I want to talk about. I want to talk about what happens when the horizon comes here and the singularity is inside, right? That's the point we want to reach about here. Yeah. So anyway, since I'm basically out trying to just rush and tell you a few things, and we can use the rest of the time for discussion. So the idea was this. So there's no horizon now. The black hole thing came and ended on the surface, right? This was the throat. It sort of ended here. I just drawn that part. And you fall on this. Suppose when you fall on this, it makes a big bump, and then the bump spreads out, just like we were doing here. Okay. Then can it possibly be that as you spread this bump spreads out, it basically mirrors this kind of dynamics to some approximation? So what does approximation mean here? Well, all the fuzzballs are different, right? Because each one is going to be a different fuzzball state because they e to the s can stand different states. So if you look at the low energy radiation from them at temperature T, they are different. That's how the information is coming out. So it's, if you probe them very carefully under a microscope, they're all going to be different. But now the point is, if you fall hard on it so that the bump you make is much more than this little Planck scale vibrations on it, suppose this bump pulls it up by 10 Planck lengths up here, then up to 90% accuracy, this is going to be the same on all the fuzzballs. And the question we're asking is, the further spreading of this, if you look at the space of whatever happened, this is just a cartoon, I'm going to tell you a little bit more about what should happen here. The entire evolution of the fuzzball state, this huge evolution in this whole space of fuzzballs, whatever this thing is, if that whole evolution, in the limit of E being much bigger than T, where they sort of can become universal, because at E of the order of T it's not universal, if that particular spreading over there, if that can be mapped by an ADS-CFT kind of duality to simple radial infall to some approximation, then I have complementarity. So I'm going to show you in the end that what we find is by doing these estimates that the error that you get, suppose you're falling with energy E and the temperature is T, then temperature of a big black hole is very low. So let's just assume it's very low. So you take E over T. Suppose E over T is some number 1 million. Then E over T to the minus a half is your accuracy of how smoothly you can actually map this onto this. So it's not exact complementarity. E over T to the half, if E over T is 1 million, then it's 1,000, the square root. So up to 0.1%, you will actually feel nothing.
So when you quote those numbers, you presume you can't say that unless you have some model in your mind for
we put a model. Yeah. Yeah, we put a model.
So what is the model?
These errors only come from the fact. Okay, I haven't actually got to the amps thing. It comes from the fact that the amps argument tells you that as you come near the horizon, you get burnt, right? So I'm going to show you why you don't get burnt, because that's the part I really want to talk about maybe for a couple of minutes. But there is Hawking radiation, and as you know, Don has often pointed out to me, there can be a slight burning from there. As you increase your energy more and more, that slight burning, the amount that you will get distorted by the Hawking radiation which is coming to burn you, that is E over T to the minus 1 over D minus 2 for D space time.
So that That's not true, for example, if the higher L modes are also polluted. I mean, you guys must have discussed this at some point, but
The higher L is okay here because the higher L modes basically you can just regard them as local Hawking radiation, right? If you take this as the horizon, if I go locally piece by piece, at any local piece, imagine a local thermal bath, the higher L modes are just equal to expanding the different L's in local things. So I assume a local temperature where things are going in all possible
in
ways.
the Hawking state, the higher L modes?
Daniel is asking
They're
about
fine
the modes that do not go to infinity.
Yeah.
So they are there. Yes, so you can interact with them and you will interact with them.
And if they're not in the Unruh vacuum, then E over T, E much bigger than T doesn't help you.
I'm going to show you why it does. So that's why you have to let me go there.
But when you quote numbers here, just so I understand, are you quoting numbers for a model of physics that includes...
That's right. I'm going to come back to your question.
All right.
I'm going to come back to your question.
Get to the model.
This is just very simple. This is a totally compactified string theory right now. Okay. So maybe I'll just tell you what Don often asks me, in the normal model of string theory, I suggest you to take total compactification. There's only one scale, Planck length, string length, they're all the same. But the real world we live in has a very funny fine-tuned number. The electromagnetic interactions and the gravity interactions differ by a factor of 10 to the 40. So when I say high energy, suppose I find E over T bigger than 1 will make me okay. How do you know E over T should be bigger than 1? Could it not be bigger than, I need bigger than this 10 to the 40. So could be a fixed number. So the black hole which I need to take, which I'm saying is big enough. Normally big enough means bigger than Planck mass. But what if big enough means bigger than the fine-tuning scales built in the standard model? And that's an interesting question to ask, but I don't have an answer.
What if it makes bigger than the black hole instead of our galaxy,
Right.
for example?
So this is only going to say that if you once take a fixed standard model of the world with whatever fixed numbers it has, for black holes big enough, I'm going to get my complementarity. Okay, so let's come to the crucial point. Why is it not ruled out by AMP? So I guess what I should ask you is, I haven't gotten very far with the talk at all, and that's completely fine. Just tell me when to stop, because I've taken my hour.
Yeah. Well, yeah, let's shoot for... Well, how much more time do you think you need to just spell out the...
I can spell it all out in maybe 5 minutes. If there are no questions, maybe 10 minutes.
Why don't we give Samir his 5 minutes of uninterrupted time, and then we can have discussion.
Okay, so let's see. We haven't yet come to AMPS. So I was just so far spelling out the picture. And the picture looks like this. So AMPS actually added extra assumption that you have effective field theory up to the stretched horizon. And at first that looks completely reasonable, because if you have anything like a fuzzball, it's going to end right at Planck length outside the horizon. That's the picture we're giving after all. And outside that is normal space. So why are you complaining? Okay. Well, there's a funny consequence of that, which is that this implies the horizon. If you take the stretched horizon over here, I just drawn it over here, and somehow something falls on it. This is a light-like particle coming in. And at first it looks completely reasonable to then say the following. After the particle hits on the horizon can bulge out or do something. But before the particle hits the horizon, nothing should happen.
I should pause to interject that we actually made that an explicit assumption. The way we phrased it was an explicit assumption that the stretched horizon behaved causally.
Okay.
It would not respond this way. It wasn't just an unsuspected implicit assumption. We said this is an assumption required to get this result.
That's right. Okay. So that's the assumption. And I'm just going to talk about that because let's talk a little bit about it. At first it looks completely reasonable. If a particle is coming at the speed of light, let's say radially, and this is my horizon, it's made of some material now, so it's like the surface of a planet. Till the guy comes and hits me, how do I know it is coming? Because causally light signals can't come any faster. So the horizon can respond later, but not till it has gotten hit. This is a light-like particle coming in. But look at it being from a slightly different point of view, and it looks a little strange. Because if you take a normal horizon of a black hole, as we know, it actually starts bulging out before the particle hits it, and then the particle is absorbed, and then the horizon stabilizes. Okay, so now let's ask. Normally, a stretched horizon should be a Planck length outside the normal horizon, right? So, but if I assume that the horizon is hit later on, what's going to happen is the stretched horizon will, at least for some time, be inside the actual horizon. So, is this what we want? What did we expect from the apparent horizon, from the stretched horizon? Because here we have an abstract theory, right? We don't actually have any model for what the stretched horizon should do. So we can put any assumption. I'm okay with that assumption because we have assumptions, we have results. There's nothing wrong with the calculation that AMPS did. Okay? But the question, let's ask if that assumption is what we actually want to have. Okay? And so I just want to see if I conveyed this point that, the normal horizon expands outwards first. Here it will expand out later. And in fact, you can see the whole difference will come from here. Because if you move out 1 millimeter from the horizon of a black hole, the temperature you get there at stretched horizon, 1 Planck length from the black hole is Planck temperature. 1 millimeter out is colder than out interstellar space. There's nothing there. Okay? Okay, the temperature of outer space is 0.1 millimeters away from the horizon. Just come to Planck here, it's a trivial statement. Okay, so let's just question that. If it comes out there, if the horizon moves out first out there, as the particle is coming in, there's nothing, it's very hard to get burnt. And those are the corrections of E by T that I was talking about. So let's see what happens. So again, I just put the same picture down here. But what were my difficulties with asking that the guy shouldn't respond first? There are two issues. Suppose this guy was carrying one bit of information. The stretched horizon, let's say after the halfway evaporation point is maximally entangled with everything, it presumably has entropy A by 4. I think everybody would agree with that. If one more bit lands on it and the guy expands later, at least for some time, on an area A, I have A by 4 plus 1 bits. And let's ask if that's something we want from the stretched horizon. So normally you think the stretched horizon is like packed densely with little plackets, and we don't really want that. It's very crude. We could have put 10 bits here if you wanted. But the point is, the way the horizon normally expands, this doesn't happen. If you're going to accept a new bit, it first opens up. You have all these dense plackets. As you come close, they open up and they accept a new placket on it. And then you always have the entropy is equal to the area. But here that's not happening. But the other problem also is, if the mass m lands first on it, and your stretched horizon is already here, but now you want it to go out here, you need something acausal. The surface has to move acausally out, because if the mass falls in here, you know that in this radius, there's enough mass to make a horizon at this distance. So light cones have tipped inwards, and if this is a normal surface of something, right now we're talking of it being a normal surface of something, I will need something acausal for this surface and all that's on it to be able to move outside to get back. Ultimately, when the thing stabilizes, you want a stretched horizon to get back to the outside. So in a sense, we're really asking the same questions which always come up in black hole physics. If you take the assumption that you first land on the horizon, just by causality, it looks very natural. If you first land there, and then the stretched horizon responds, it doesn't actually have the properties. It actually has one property which I wouldn't want any stretched horizon to have, maybe, and one which tells me I will need something acausal later on. Okay. So let's see what actually happened with fuzzballs. How did it get bypassed in doing the whole thing? So firstly, we are looking for E much bigger than T impacts. And if you do this, the surface actually moves out a lot. And because it moves out, there's no temperature there. As I said, these are the corrections, and the guy doesn't get burnt. So the fear was, before I can trigger this once kind of idea of ADS-CFT, you fall on a surface, you excite it, and those guys have some frequencies. Falling in radially has some frequencies. If these frequencies are equal to those frequencies, the systems are isomorphic. Okay, that was ADS-CFT. I want to borrow that idea. My fear, of course, the fear of amps here was, by the time you come to the surface, before you can activate that idea, you will get burnt by the radiation. But if the horizon bulges out before, actually the temperature is basically gone, and you won't. So as long as you want an approximate thing, it would be okay.
What, you have an E, a T, and a 1 millimeter. How are these things related?
Yeah, so this one is actually simple. As you go away from the horizon, there's no E in that one. At Planck length from the horizon, the temperature is Planck. At 2 Planck length, the temperature is Planck energy by 2, and so on.
How big a black hole are we talking about?
In this one, the size doesn't matter.
Doesn't matter.
If you go distance d from the horizon, the wavelength at that distance is of order d. Okay. Right? So if you go 1 millimeter outside the horizon, the wavelength is 1 millimeter. And then if you take 3 degree Kelvin, the wavelength for that is just less than 1 millimeter. That's all.
Not the firewall, though.
Pardon?
That effect is not the firewall.
That's exactly the thing.
It's true in Minkowski's space.
That's what I think. You won't get a firewall there. At 1 millimeter, you don't have a firewall.
That was not claimed to be the firewall.
So the point is, how did you bypass the firewall here? The firewall is supposed to be the fact as you come close to the surface, the high energy quanta here will burn you. But now what has happened instead? As you came close to the surface...
That's not the firewall. The firewall is after you cross the horizon, then the entanglement between those modes and the ones on the other side is incorrect.
I'm coming to the entanglement. Yeah. So let's see. So because here we're not going to get the firewall for a very different reason. Yeah.
I'm just getting confused now, because you're talking about the unroot. An accelerated observer sees those temperatures, an infalling observer doesn't. So somebody falling in arbitrarily close to the horizon doesn't see these huge temperatures.
I'm glad you asked that. That was the whole point of the firewall thing, right? That if you actually have a real surface there, which can radiate, if you had the normal vacuum, you have the information problem. If you actually had a surface like the fuzzball people would claim, that you actually have a surface, and that surface is emitting stuff, then things were immediately different, because that stuff would be really very hot. And that is true. If that surface didn't move and I was trying to come to it, and I claimed when I hit the surface, I get Huan's ADS-CFT kind of idea, I can't do it. But the important thing is, if I'm keeping track of the energy I'm coming at, and if my energy is 100 times the temperature, then the surface will bulge out to meet me at 10 Planck length. There is no temperature there. So at least I can have my complementarity, And now let's see what the other steps
Sorry,
are.
but if there was a high energy photon coming up there, okay, it doesn't matter that the event horizon moved out a little bit, I still get clobbered by it. I mean, are you just saying that you can't be held responsible for anything that happens behind the new horizon?
The new horizon. So okay.
The horizon moves out, but I mean, there was the place where the horizon...
So there is no horizon here. See, what moved out is this surface. And this is the first-ball surface where space-time ends. So
So then you're pleading the fifth. You're saying that you can't, that, we're not allowed to discuss anything beyond...
No, let me just explain the picture. Let me just finish the picture, because let me just have my 5 minutes to show what the picture was. So then the whole entanglement story was, the black hole is maximally entangled with the radiation, and that's why you can't get things to work. However, with the first one, what we are doing is, we're taking energy much bigger than the temperature. When you throw in something with energy much bigger than the temperature, you've added energy to the black hole. When you add energy to the black hole, actually you have more states than before. In fact, that's how you would compute the number of new states divided by the number of old states. And if you just follow this algebra, which is completely trivial, you'll find that the new states are much more than the number of old states. So when the stuff comes and falls onto it, this is the kind of thing that the Verlanders have also talked about. When you actually fall on it with E much bigger than T, you're going to create new bits. And the entire evolution that I'm drawing here is the evolution of these new bits. So how these new bits spread out, they're not entangled with anybody. That's the one to which I want to apply one's ADS CFT idea to. Yeah.
How does your monopole picture do this actually?
Yeah, so what happens is, so here you have, all the compact dimensions are coming and sort of pinching off here, right? When you add extra energy...
But can you get this from a solution?
Can you get what?
Why does the monopole behave different than a causal stretch horizon like the AMPS people are using? Because I think that...
Why does it expand out first? That I'm going to show you. I haven't showed you that. That I have to show you, right? So right now I'm just saying that it was reasonable to ask the stretch horizon to move out first, because otherwise I had these issues. I haven't told you how it would, but... So that's the point which I was doing. I don't have time to do any of this, but let me just go to the final picture so I can show you what the idea was. The idea, so this goes back to what I showed you here, that as you come near here, if you knew the mass of this guy, you can find out at what distance these transitions start happening, because the transition amplitude is estimated by this Cross and Wilczek kind of thing, and then you have the degeneracy of states. So as you start coming, this is now the answer to your question, as you start approaching where the horizon was, for the horizon was at this blackboard here, and I'm coming here. If I had more energy, wherever the threshold is to make the horizon, at that threshold you'll find that the fuzzball states you can transition to are actually on shell. So as you come here, you slow down, but your amplitude starts moving into the fuzzball states. So it all starts happening depending on what energy you have at the place where the horizon, new horizon would have formed. So in fact, it's not like you first ever go through that into the old horizon. You never go in there. So let's put the full picture down here. Okay. Let me just skip as many things as I can. So this is the overall picture. So as you're coming closer in here, let me see what I summarized here, because I've skipped a lot of stuff. So this is the picture. As you come close to the horizon, you basically spread over the space of fuzzball states, which I was drawing here. You study the rest of the evolution entirely in superspace, the space of all these solutions, not in one metric, and the entire evolution in the superspace, which I've drawn here. There's some abstract representation of superspace. That you would like to conjecture is approximately equal to the radial wave equation, which is going in one black hole. So here, for example, this is the analog of all the little open strings, the complete mess you saw spreading in ADS CFT on a slice. Now you're actually working in the space of all these gravity solutions. So as you come there, you start transitioning into all these solutions like this. There's almost equal amplitude to go to pretty much all of them. Like it's just sort of, that's why I've drawn them as...
E and T are measured at infinity here?
That's a very good question. In fact, I had a slide about it, which I skipped. E and T are measured everywhere in exactly the same way. And here. So at infinity, the mode starts off with a wavelength equal to the Hawking wavelength. As it comes close, the wavelength decreases. But that's also equal to the local Hawking temperature. When you come to Planck length, it becomes Planck length. And that's equal to local Hawking temperature there. So this is what I call an E of the order of T mode. So if at this point you have a mode which is 10 times this particular wavelength, I'll call it E much bigger than T. That's the definition. Okay. So because I promised to stop in 5 minutes, let me just go ahead and do that and see if I can put some final slide up. I've skipped most of the things I was going to tell you, but that's just fine. If you must make a Penrose diagram, I don't like to make them, because what happened is Penrose diagram is for one solution, but the physics here was as you come close, you spread over the space of a huge number of solutions. That's what has really changed everything. So you can't come close. As you come close, the redshift freezes you. And as you freeze, you start evolving into other directions. In a theory without fuzzballs, there's nowhere else to go. You'll freeze, come closer, sort of asymptotically, like the Zeno's paradox. And then if you want, you can continue inside. That's the critical change. But as you come closer, if your amplitude starts spreading in completely different directions, it's a whole different ballgame. And that happens at this new horizon. So the difference from amps is you never actually go in. There is no in to go into. Let me just write that. I had a final slide where I showed what goes wrong in amps.
The observer feels that he goes in or not?
The observer feels that he's going in. So exactly like the ADS-CFT. You've gone and you've gotten broken into all these different solutions. So if you actually write all the solutions in a computer, you will actually see that they're just spreading on the surface. But if you want to approximate that by a dual behavior, the spreading over this superspace of solutions, that should have the same equation as the equation of going in, exactly like ADS-CFT. That would be the conjecture.
You're asserting some kind of integrity of the infalling observer, but where does that come from? Can you?
It's exactly the same way it came in ADS-CFT. There also you broke up into lots of open strings, right? But it's just a kind of it's not easy to prove that you're going to do that, right? It doesn't work for a generic theory.
Some magic had to happen, and how do you know the same magic happens here?
You don't.
Even if it happens there.
You don't know that the magic happens here. I was only going to show you a scenario where you can get your complementarity, right? In ADS-CFT also, I don't know how to prove it happens, apart from the fact that now we can check so many cases.
Let's see, many of the amps problems arise if you think that the interior, right? So is there a map between the observations this guy makes in the interior to the Hilbert space, microstates of the interior? So
good, let's talk about that. So let me just open up my Penrose diagram again. So this is the key, right? So the actual shock wave comes, but as you come here, because spreading over fuzzball states, this is the white part of the actual space which is there. Now, the interior region, I've only drawn with these arrows and shaded. If you put the whole thing in a computer, this part of the space is not there, right? Because all the microstates ended like bubbles of nothing. There's nothing in there.
Can you use a computer to calculate the experiences of an observer who falls in?
Yes. So I've drawn these with arrows going this way because this space only exists for modes which are actually coming in hard with E much bigger than T going left. It doesn't work, for example, for modes which are E of the order of T, which are like sort of moving to the right. So a space in which you can only see valid for certain kinematic domain, but not for all the kinematic domains. That's what I've drawn by the shaded region with arrows. So when you ask your question, you've got to be precise. If you're going to say, I want a particle going this way, that particle is not captured by this approximation. So that's how I'm going to get out of all the puzzles, that only for this kinematic domain of fast-falling particles, this effective space-time emerges, and then all the puzzles you ask about a guy going to the right, a guy going to the left, then those puzzles I'll try to avoid in that way.
The guy who falls in, he can measure naively modes that go to the right. And in fact, modes that go to the right with E of order T are important for his experience falling in, right?
So here the claim is that unless you have done something very fine-tuned with the initial fuzzball, like you can always make a fuzzball is ejecting a particle to burn you or something, right? Unless you've done something special to the fuzzball, as you fall in, there will be nothing to measure. He'll feel that it's not a state where some particle is actually trying to come out. Okay, so if you want to make a state where the particle was coming out to kill him, in the whole space of fuzzball solutions, you could really fine-tune something, and then you can do that.
So is there an operator acting on the Hilbert space of the microstates, which corresponds to the occupation, that can tell whether or not you made one of those particles going up? Is there a linear operator like that?
More than that, I think if I fall in...
there's an argument that there's
I have not tried to make one, so I don't know.
There are arguments that there isn't, but then there's a question of what does it mean to say that this guy can or cannot see this?
So the only thing I can tell you right now is that the E of the order of T modes, which are the ones going right, which are the part of the Hawking radiation, they are not reproduced in the approximation I'm using because only E much bigger than T impacts have done this approximation.
But the guy, if you screw them up, that guy will see them. So
no, there's nothing to screw because it's not like this is a space-time which has left and right moving guys.
You said there are states where I excite them, right?
You can make states where this doesn't happen, so it does something else. If you want to, because if I've just assumed you fall on the fuzzball and the fuzzball does something, right? If the initial fuzzball wasn't a generic one but had, let's say, a spike sticking out, then everything is different, right? So on that, what you feel, if you want to interpret that as something else happening in here, okay, I have nothing to say, but this is all effectively derived from the fuzzball. So all one is saying is that the generic space of all fuzzballs, the superspace of all solutions, you really get pushed into the dynamics of working on this superspace because the transitions, once you come within the black hole radius, close to it, there's a spread over all these possible states. And so this enormously large superspace of e to the s Beckstein states, your whole wave functional is spreading on it. Exactly like all the whole space of open string, this enormous number of n squared degrees of freedom, a wave functional is spreading. Somewhere from that we extract something falling radially into the throat. And that's what one is trying to say here. One wants to generalize that idea and just say that approximately the entire spread over superspace is going to be such that it's going to be approximated by infall readily into the black hole. So it's a very different spaces. But the fact you go over superspace is because these transition amplitudes I was showing you. You come near the black hole threshold, it automatically happens. I'll stop here because I had promised to, but if there is still time left, I would like to show you this particular thing which I had made here. But let me just stop here, just to not abuse your patience here. Yes.
Discussion.
Yes, I want to make a comment that relates to the questions that Samir was asked. I actually like a lot of things about what we heard in this talk. But I think something that's really important is what Samir said about how the space behind the horizon into which the infalling observer falls is actually created by the infalling observer. It's not something you can think of as there, think of operators that exist in that space. It doesn't happen until something actually comes in, and it has to be something that satisfies the kind of kinematics that he was talking about. Now, there's a little piece of evidence that a picture like this might make sense that comes from things that are well known, and I think everybody agrees to them because they're part of classical GR. If you look at what happens when I drop something onto a black hole, as looked at from an infalling trajectory, but which has not yet fallen onto the black hole, then you see things happening on the horizon. And you see the horizon gets disturbed. It's no longer spherical if I threw something in some state that's angularly localized. And then it takes quite a long time for that to spread and to come back to equilibrium. And in the picture that Willie and I have tried to develop, that really is dual to the inside of the black hole. And in the same way, it's something that gets created by a particular initial state, and it exists only for a time of order the Schwarzschild radius after that initial state crosses, quote, the horizon. And it's not the same horizon because things have changed. You can't think about it in a classical way. But there has to be dynamics in whatever our quantum theory is that describes the thing that we call quasi-normal modes in classical GR. The fact that when I ping the horizon, something happens, it changes, and then that change goes away after a time of order Schwarzschild radius. And I think one of the things Samir is saying is that that's really what creates what we call the dynamics inside the horizon. And I think that picture will turn out to be correct.
Yeah, I like to second that because it's indeed sort of the thermalization process that the observer feels when he goes in. That's actually describing the physics behind the horizon. And it's only when he's completely thermalized and he's back to, so the fact that he's not immediately thermalized is because you don't interact so enormously hard with all of those degrees of freedom. It's not like you at the horizon you hit and you suddenly thermalized. You are out of equilibrium and you will stay out of equilibrium for a certain amount of time, and then you get the thermalization happens, and this is where your physics indeed stops, and that's the singularity that you need. From the outside, of course, is very different because then you see this person sort of freezing at the horizon and you see the thermalization happening there. And that's the complementary picture.
So I absolutely agree with this. One thing you said is very, very important, the last part you said, because I think that was is very crucial here. So when you fall and you get this collective oscillation in the beginning with large amplitude, where you're trying to map to the area safety kind of thing, at some point they dissipate, exactly as you're saying. Because the thermal system, they don't live that long. The coherence will go. And the conventional thing would be to say that that's when you reach the singularity, because you can't maintain this kind of thing for too long a time, and then you've decided. Right?
Let me ask a question. So imagine you fall into the black hole carrying a spin, and you measure it after you cross the horizon. Do you think there is an operator in the boundary theory that, or in the space of microstates that's measuring the spin that is describing this process? The outcome
I would like to think yes. It's a freely falling spin. It fell in like hard.
Yes,
not like gently
together with an observer, so that we have energy much bigger than it. So the observer has energy much bigger than it, but carries a spin which is just a single quantum degree of freedom.
So you can't ever talk about measuring the outcome of that experiment because that process, what you call the outcome of that experiment, is you've thrown some macroscopic thing in with the spin, which has become correlated with the spin, and you think about the state of that macroscopic thing as something that actually happens. But the quantum state is still the superposition of that with the Schrodinger's cat state, where you measure the other spin.
Well, for you,
and the outside observer can never see that.
Well, let's see.
The outside observer sees that having unhappened.
Well, let's see. So if I'm in a closed system and I do this experiment, I also will be in the superposition of two states. One is having measured the spin up and one having measured the spin down.
Right.
And normally what we would say is that, well, these two states decohere enough so that we can call them
But when the information, this is, Charles Bennett gives this talk all the time. He shows you a picture of some footprints that were made in the desert in 1920. And those footprints still exist because we have this macroscopic photograph of them. But we don't know whether those footprints really exist or not. Eventually, all the information about those footprints is in the radiation that was emitted when the footprints were made. And eventually that radiation is no longer encoded in the collective coordinates of a big macroscopic system. It's in the state of a lot of photons way off in distant galaxies. And at that point, that footprint doesn't exist anymore. The predictions of quantum mechanics are that quantum mechanics never makes predictions about definite things happening. It only makes predictions about the probabilities of things happening. And when we talk about unitarity, that just means what happens to that probability distribution.
Maybe another way to phrase the question is, I carry in two spins in some entangled state, and the energy differences between this state and some other states are much less than the Hawking temperature. Are those two spins going to remain in that state, or is this as we fall in, or is the Hawking temperature?
No, I think I would like them to remain in that state as long as they fell in freely, so that when the center of mass energy, when they hit the horizon, was high. So then, as they never reach near the horizon to get burned by the radiation. Quite far away, you are on shell to start tunneling into these new states, and then all your information now holographically encoded in the huge superspace wave functional, which is now spreading out from that region. And that huge superspace wave functional spreading out as per those green circles I was drawing, that can encode everything, because the correction always just says e over t to the minus 1 over t by 2. So I would like to think the answer is yes, because I would like to say at the end that if the black hole is big enough, at the end of the story, that if I fall sufficiently far away into a black hole big enough, if I'm drinking my cup of coffee, I shouldn't feel anything up to these corrections. And apart from the fact the standard model could have big numbers, the black holes should be really big and all that. So up to that fact, I would like to say that everything you do with your cup of coffee should be there.
So when we talk about small corrections, you mean like small powers of E over T?
Yeah. So we put bounds on this E over T powers. We only got powers. Yeah.
Well, because what I wonder is.
But these are bounds. I'm sure somebody can do better. We didn't try to.
Okay, but so any deviation which is small, like a power in G Newton, is still it's an observable deviation from perturbative effective field theory in a place where we might not have expected it, right? So I mean, at that point, shouldn't we just call it a firewall? I mean, to me, the definition of firewall is a deviation from perturbative canonical gravity.
But you have a different definition of firewall than the firewall.
You have to be very careful when you say something like that, because you certainly don't want to be talking about things in effective field theory that involve measuring huge number of point correlation functions.
No, I don't mean that. I mean like
you want to be talking about the actual experiments that an actual system thrown in with a certain energy could actually do.
Yeah, so that's what I'm asking. And are there deviations there at the level
you certainly expect deviations that go like powers over G.
I mean, not like tidal forces.
Let's make this concrete, right? I mean, there's a discussion that Samir and I had before about if we enact the model as written. If we take this model more or less as written, we try to use the physics of the standard model. And now I myself jump into the black hole of our galaxy. Do I survive or not? And I think our last conversation was, if we interpret exactly what you've written in a straightforward way, the answer is I don't.
Yeah, so let me just concretize what...
There are effects that are formally small, but can still be definitely detectable. It could kill me in a context where I might have hoped that the infall was smooth and free.
Yeah, so let me just explain that. A large part of this is something we had done 2 years ago in this paper with Turton, and at that time we had a whole discussion with Don. So the status is this, like as I was saying, in the standard model we had this very crazy factors which come because some compactification of our universe being a little asymmetric, so that all the forces are not of the order of the gravitational force, which you might normally expect for a unified theory of gravity. So if you have some big number like 10 to the 40 sitting somewhere in the compactification, then are the corrections e over t to the minus a half, or are they 10 to the 40 times e over t to the minus a half? Okay. So we never try to do that. Okay.
I mean, either way, effective field theory is wrong.
Yeah, but that's different from what there's a question of scales. Some small violation of effective field theory will not necessarily kill you.
I don't care whether I get killed. I care whether
you have a way of organizing how.
So that we have agreed with Don. Don said it. In fact, one thing that Don put in there.
The firewall story involved quanta that were very high energy hitting you, and it's a question of scales. You're running into high energy quanta, low.
So as you fall more and more energy, so let me just finish with what Don was saying. So if I got e over t to the minus a half, but suppose it was 10 to the 40 e over 2 to the minus a half, then I have to say, okay, as long as my black hole becomes bigger and bigger, I'm still okay, right? Because I fix my E, I fix my object, and t is just like 1 over m. So as the m is bigger, I'll be okay. But at what point does the e over t to the minus half times 10 to the 40 become less than 1? And 10 to the 40 is a very big number, because in Planck masses, even the galactic black hole would be still 4 to 1. So you get very funny scales. Normally we used to think that 10 Planck mass is big enough to get 10% accuracy. But if there's a funny number like 10 to the 40 hiding in somewhere, then you may not. So when we were doing these calculations about trying to see how much the errors were of colliding with something, and we had this e over t to the minus a half, then Don pointed out that, look, if you use the other interactions, which are not the gravity ones which you take from string theory, but suppose you assume something in the comparison is fine-tuned to be 10 to the 40 times that, and then put in the numbers, then indeed we'll get 10 to the 40 times e to the minus. So then the black hole has to be really, very big. As a matter of principle, it's all still exactly what I said. But as a matter of practice, it's very interesting to ask. I should also mention that there's a nice paper of Don with Virmani and somebody else, which actually...
From some years ago.
What?
Aaron Amsel from some years ago.
Okay, so as you come in, you want to know how much the horizon bulges. So order of magnitude is easy to estimate, but if you actually want the shape, they have a computation in that. So it's...
But that particular factor of 10 to the 40 has to do with your particular model of what the states are on the horizon, right?
Yeah, it has nothing to do with states. It's the compactification of you take some string compactification, the answers, the exact numerical numbers can depend on the compactification.
Yeah, that for sure, but if the states are not something that I associate with particular solutions in string theory, I don't see how we can do that calculation and know whether
it has to do with his model of the space that is created, if you will, by the infall observer, corresponding to the change in the classical GR event horizon. It's that scale, the scale at which the event horizon grows in response to the infall observer, that sets the magnitude of the...
So just what, it wasn't exactly there. So as you come in, how much the event horizon grows, that's just fixed by the mass, that's just gravity.
Yeah.
But what are the interactions with the outcoming particles? That's what you want to put binds on, right?
The standard model, it's the standard
and that will be higher in the standard
together
model.
with this model of what is the region of space being created.
Yeah, so I think I'm just clarifying because I think Tom was asking a different thing. How much it bulges out has nothing to do with what the standard model is, because that's just gravity.
The two put together.
Right. But
this is the new space.
The outgoing, the outgoing guys with the ingoing guys, how hard they bounce against each other to get the corrections. I just use the gravity-gravity interaction because it's all unified. In fact, we used an old paper of Tom about black hole cross-sections.
You're using a model in which the states consist of the thermal atmosphere of the black hole. What is the model of these states that you're using?
Yeah, I think this has become a small discussion, so let's formally break unless there are other pressing questions, and then this can continue. And let's thank Samir again.